We learned in the previous session that light is a form of electromagnetic wave. Whether it is directly visible to us or not, all electromagnetic waves are different forms of light, or interchangeably, all forms of light are different types of electromagnetic wave. So how do we classify the various types of electromagnetic wave, the various kinds of light that we encounter in our lives and during work? Let's say that we are encountering light at very, very low frequencies, right? An electromagnetic wave can have very low frequencies. For example, the AC, alternating current supply in our home, is operating at just 50 hertz. So is 50 hertz enough to classify it as an electromagnetic wave? Yes. The wires around you, the equipment around you is radiating energy in the form of electromagnetic waves at a frequency of 50 hertz. In fact, you may have often heard the signal coming from these power lines in the form of a buzz in your earphones. So even that low frequency electromagnetic wave is a form of light, even though we are not able to see it directly. So starting from the absolutely lowest frequencies that we can imagine, so what is the point of ELF? Aside from being a nuisance in our earphones, does it have any practical use? The interesting thing is, extremely low frequencies of electromagnetic wave are not absorbed very easily. They are not absorbed by land, they are not absorbed by water, they are not absorbed by air. So if you want to communicate using electromagnetic waves with something that is under the ground or under water, ELF waves are a useful method of doing so. For example, military submarines communicate with surface vessels using ELF, or extremely low frequency waves. When we increase the frequency of these waves, we are now reaching a region of the electromagnetic spectrum, the set of frequencies that we are going to study, that is known as the radio frequency region or radio waves. Remember, the electromagnetic spectrum is a continuous spread of frequencies starting from 0 hertz to a very, very, very high value. So in this case, this region of the spectrum, which ranges from about 500 kilohertz to about 1000 megahertz, is known as the radio wave region, or simply radio waves. So the frequency of this region extends from about 500 kilohertz all the way to about 1000 megahertz or 1 gigahertz. The AM band, which is, I am sure, familiar to most of you, is starting out at about 530 kilohertz and extends to about 1710 kilohertz. Once we go beyond this, we reach the FM band. The FM band, as you know, is around 90 to about 500 megahertz or half a gigahertz. Further on, we also have things called shortwave, VHF and UHF, which are used by televisions and military radio systems respectively. Beyond this, when we further increase the frequency, we reach a region of the spectrum that we call microwaves. Now, microwaves extend into the gigahertz region. For example, the household microwave oven that you use to cook food is generating waves at about 2.4 gigahertz. Interestingly, this frequency coincides with the region of the spectrum which is most readily absorbed by water. Anything that contains water, like fruits or vegetables or meat, will readily absorb microwave energy and convert that energy into heat. And that is why a microwave oven works. In addition, microwaves are also used in applications like radar. For example, if you want to find the distance and speed of an object far away, you can fire a microwave at it, and from the reflection, you can find out how far the object is and at what speed it is moving. You can also use microwaves for high-speed communication. So if you have two microwave receivers and transmitters, you can transmit information at a very high rate between them. Now, as we continue to increase our frequencies, we reach a region of the spectrum called the infrared or IR region. So the next region of interest is infrared or IR region. Now, this region is also known by the name of heat waves or heat radiation. Now, it is important to remember that heat waves is something of a misnomer. It is not as if IR waves themselves are hot. The reason they are called heat waves is because, number one, any material whose temperature is above 0 Kelvin will be emitting some energy in the IR range. So any object which has temperature will be emitting energy in the form of infrared radiation. The second reason is that infrared radiation is also readily absorbed by any material containing water. So any object in daily life which contains water, on absorbing IR waves will become hotter. So IR waves, even though they themselves are not heat energy, have a heating effect on many common materials. It is for these two reasons that we call infrared waves heat waves or heat radiation. We have just reached the portion of the spectrum where our eyes become sensitive enough to see energy directly, to see electromagnetic waves directly. And this region of the spectrum is what we call the visible region. The visible region extends from the color red all the way to the color violet. So in terms of frequencies, the visible range of light extends from about 4 times 10 to the power 14 hertz all the way to 7 times 10 to the power 14 hertz. If you want to talk in terms of wavelength, this range extends from 700 nanometers for red to about 400 nanometers for violet light. This region or this portion of the spectrum is the one where the human eye has maximum sensitivity. However, it is important to remember that we are not sensitive to all types of visible light equally. If you were to measure sensitivity of the human eye, you would notice that our eyes are most sensitive to light which is green in color, which looks green to our eyes. Now, it is important to remember that while the entire visible region of the spectrum is visible to us, the sensitivity of our eyes is not the same for every color. The peak sensitivity of the human eye is around the same region of wavelength which corresponds to the green color. This is why often night vision devices are green tinted, because our eyes have maximum sensitivity to that range of frequency and wavelength. So far we have reviewed low frequencies, we have reviewed radio frequencies, microwaves, we came to infrared, and then we came to the visible region of light. Now again, as we keep on increasing frequencies, our eyes are no longer able to detect the light directly, but these frequencies still have various bad effects on human physiology, as you will see. So as we go beyond violet light, we enter a new region. The new region that we enter is known as UV, which literally means ultraviolet. So those range of frequencies which exceed that of the violet color, or those range of wavelengths which are less than that of the violet color, constitute the UV region. UV light can be produced in two ways. If we heat materials to a high temperature, they will start emitting some of the energy in the form of ultraviolet radiation. Another way is to ionize various gases to produce the ultraviolet light. That is the principle on which UV lamps will operate. The sun, being a very hot object, is producing a considerable amount of energy in the UV spectrum. And the reason that we are not directly affected by this UV light is because of the protective layer of ozone around the Earth's atmosphere, which absorbs and blocks the UV radiation. Ultraviolet radiation is ionizing. So what happens is that if this radiation comes in contact with living tissue, it will cause ionization of the materials in the tissue. It can cause damage. It causes sunburn in people who have low amounts of melanin in their skin. It can also cause skin cancer due to prolonged exposure. This is why people who are living at high altitudes suffer from things like cataracts or increased rates of skin cancer, because they are getting more UV at that altitude compared to people living at sea level. Now, UV light has a rather broad range of wavelengths. It extends all the way from 400 nanometers to just 0.6 nanometers. So a very large region of the spectrum is classified as UV light. Once we go beyond UV, we enter the region known as X-rays. So I'm sure all of you have heard of X-rays. X-rays have extremely small wavelengths of the order of 10 to the power minus 8 to 10 to the power minus 13 nanometers. X-rays are produced by various methods. Nuclear reactions produce X-rays. You can also produce X-rays by firing extremely high energy electrons into dense materials. For example, the X-ray systems in the old days had a tungsten target. Tungsten is a very dense, very hard material. If you fire high energy electrons into the tungsten material, the tungsten will start emitting X-rays. X-rays have extremely high penetration power. They can go through human tissue, they can go through bones, and that is the principle that we use for X-ray imaging to detect fractures or other pathologies. Once we go beyond the X-ray range, now we enter a new region known as the gamma region. So these are known as gamma rays. Gamma rays can only be produced by extremely high energy nuclear reactions. They have extreme penetration power. They can travel through several feet of lead, and they have extremely bad effects on human tissue. They can cause radiation poisoning and even death. There is a lot of gamma radiation coming from outer space because of the nuclear reactions happening inside the sun. However, most of these gamma rays are blocked by the Earth's atmosphere. So that should give you at least a cursory understanding of how varied the electromagnetic spectrum is and how different behaviors are seen in different kinds of light.
Manorama Horizon. Learning made simple.